Hello everyone, welcome to this lesson. So in this lesson, we're going to go through the second numerical method to find 1D optimums, and that's going to be called the golden section search technique. Now, if you remember in the previous couple of lessons, we have gone through the Newton-Raphson, which is originally a root finding technique, and we found that if we took this root finding technique and we applied it to a derivative of a function, we in consequence find the optimums of the original function. Now, the golden section search actually mirrors a little bit or has similarities to a few root finding techniques, and specifically bracketing methods. The bisection and false position is because the golden section search also brackets the optimum when it attempts to find it. So actually, let's begin. So the golden section search actually gets its name because it employs a ratio called the golden ratio, which is a very famous ratio in nature. It actually follows the Fibonacci sequence, if you've heard of it. And also, it's also called the ratio of beauty. Anything that follows this ratio, we find it more appealing, and anything that deviates from it, we find it less appealing. So we're going to be going through 3 different iterations for the golden section search. And if you look at the first iteration, for example, you're going to find that much like with the bisection and false position, we're going to be bracketing the root. In this case, I'm going to be using a lower limit of -1 or -2 and an upper limit of 1. And if you look into this section here between the upper limit and lower limit, you can find that I have x1 and x2. And these are analogous to the estimate, the root estimate that we got for the bisection of false position. But in this case, we're getting 2, x1 and x2. And if you look at the further left here, x1 is the lower limit plus d, and x2 is the upper limit minus d. So what is d? Well, d is the golden ratio, which is square root of 5 minus 1 divided by 2. So in decimal form, it's 0.61803 multiplied by the upper limit minus the lower limit. So you get d, and from d and also the upper lower limit, you can get x1 and x2. So if we apply this quantitatively, you're going to find that d, given that I have an upper limit and lower limit of 1 and -2, I get a d of 1.854, and given I have d and the upper and lower limit, I have x1 to be -0.146 and x2 to be -0.854, and you can find they're here. So once we get the x1 and x2, we have to actually evaluate the function values of both. So you find the function value of x1 is 3.98 and the function value of x2 is 3.395. And since we're getting a maximum here, the optimum is going to be corresponding to the one that has the highest function value, which means the optimum here is 0.146. And given that my optimum here is 0, it is somewhat of a good approximation, as you see here. Much like we did with the bisection of false position, we're going to be choosing the section in which the optimum is, and you find that since the optimum we said is at x1 here, we're going to take this section between x2 and the upper limit. So we're going to be taking this. So as you probably have predicted, x2 here becomes the lower limit, as you can see down here. And also if you look here, x2 is closer to the lower limit, which means what was formerly x1 becomes x2. So in the second iteration, we have the lower limit, we have x2, and we have the upper limit, which means we have to calculate the new x1. Now, if you look at the d here depends on the upper limit and the lower limit, or the difference between them. And since in the second iteration, this upper and lower limit changed, that means d changes with each iteration since that interval changes. So in this case, if you look here, the lower limit is now -0.854 and the upper limit is still 1. So that gives us a d of 1.146. And from that, we can calculate basically the new x and the new x1. So x1 here is the lower limit plus d, and here you can see that our new lower limit is 0.854 plus the d that we have gotten here, 1.146, which gives us an x1 of 0.292. So you can find that we have here 0.292. So what we're going to do is we're going to get the function value at x1 and x2 again, because the one that has the highest function value, which will be the one corresponding to the x optimum. So x1 is 3.9098 and this one is 3.98, which means the optimum is still at x2 in this case at 0.146. So we're still hovering around the same optimum, but you can see that we started with a section that is -2 to 1, and now it's just negative 0.854 to 1. So we're zeroing in or narrowing down. So now we're going to be choosing the section in which the optimum is, and we hear the optimum, the estimate is xx2, which means the section is between x1 and the lower limit now, and which means x1 becomes the upper limit, as you can see here. So now the upper limit is now at 0.292 and the lower limit at negative 0.854. And much like what we did here, what's closest to the upper limit is x1, which means this, what was formerly x2, is going to become x1. And much like we did with the second iteration, we're going to calculate the new x2. And before we calculate the new x2, which is defined as the upper limit minus d, we have to calculate the new d, because, you know, the distance between the upper and lower limit has changed. So we calculate the new d. The upper limit is 0.292, lower limit is negative 0.854. That gives us a new d of 0.708. And we use this to get the new x2, which is the upper limit at 0.292 minus d at 0.708, which gives us negative 0.416. So now we get the function value at the upper and lower limit, and that gives us at x1 is 3.98, at x2 is 3.813, and you can find that the optimum is still at the function value x1, which is in this case still negative 0.146. So this pattern you can actually see when you're using the golden section search. Usually we're narrowing down, but we're still hovering around the same optimum for a few iterations. So here we are stuck at 0.146 for 3 iterations, and at a certain point the 4th iteration is going to change and is going to get stuck there for the 5th and 6th, then it's going to change and so on. But nonetheless, as we are doing this, we are zeroing in and closing in the section more and more. As you can see here, we started -2 to 1, then we started reduced it to negative 0.854 and 1, and now is negative 0.854 and 0.292. And if you see here, if we predicted what's going to happen for the 4th iteration, you're going to find that here x1 is where optimum is, so our new section is going to be between x2 and the upper limit, which means x2 here becomes our lower limit, and x1 here becomes gets replaced with x2, and now we calculate the new x1. So basically we replicate what we've done with the second iteration here. So we're going to keep doing that over and over again until the x optimum gets below the 0.1% error, and we converge to the maximum here at 0. And this is done similarly to basically the minimum, but the only difference between the maximum and the minimum is instead of taking the maximum, basically taking the highest function value as the optimum, you're going to take the lowest function value as the better estimate for the minimum. So the only difference between the golden section search code to find maximum and to find minimum is whether you are comparing the two function values as greater than or less than. So the change in the code between a minimum and a maximum is just going to be a change in sign between functions, and we're going to see this more clearly in the next lesson. The last thing that I do want to end with is describe that the definition of the approximate error for this golden section search technique is slightly different. is basically 1 minus the golden ratio, and this is the absolute value of the upper and lower limit, the difference between them, divided by the x optimum multiplied by 100. So this is how we're going to be defining the approximate error in this code, as opposed to the previous codes, which was the new minus the old divided by the new, as we have been accustomed to. So that's it for this lesson. In the next lesson, again, we're going to be creating the Python code to replicate what we have done in these 3 iterations. So thank you very much, and I will see you in the next lecture.